Welcome back to Lanthanides. So we were discussing extraction and lanthanide oxides were obtained. So cerium was completely oxidized, and the oxides were in the form of mixture containing 50% cerium oxides, 20% neodymium oxide, 17% lanthanum oxide, 8% praseodymium oxide, and 5% samarium oxide. The mixture of these oxide was treated with dilute nitric acid. And what happened with dilute nitric acid? Cerium oxide was insoluble, uh, and rest of the lanthanide oxides, they were soluble in this dilute nitric acid. The resultant insoluble cerium oxide can be filtered from the solution, and the crude cerium oxide can be obtained. Now, the solution contains rest of the lanthanide oxides, while solid portion or precipitate contain crude cerium oxide, which can be separated easily with the help of filtration. This crude cerium oxide, if it is treated with 85% nitric acid, which is far more stronger than the dilute nitric acid, so in the presence of this strong nitric acid, cerium oxide gets dissolved and a solution can be obtained. Upon treatment with excess of H2SO4, the precipitates of red basic nitrates of cerium can be obtained. What is the purpose of addition of this sulfuric acid? In order to get this red basic nitrates of the cerium, the resultant cerium, and it is in hydrated form. So the cerium can further be processed for purification, and rest of the elements in oxide form, which we obtained in solution form in this step, they can also be processed for separation of respective lanthanide accordingly. Now, let's summarize the whole process. So, what we did, we started with monazite sand, which was actually phosphate of lanthanide, lanthanum, thorium, cerium, praseodymium, neodymium, some D block elements like thorium, yttrium, and some heavy metals as impurities. The monazite sand was crushed into powder in order to increase the surface area for reaction. It was treated with concentrated H2SO4 at high temperature, and a paste of lanthanide sulfates and phosphoric acid can be obtained. This paste is now treated with cold water, and upon treatment with cold water, we can get solid silica and zirconia, which can be separated by filtration from the solution, and the solution contains sulfates of lanthanides plus phosphoric acid. Now, this solution can be diluted with water. pH of the solution can be adjusted in alkaline range, and if you remember, the lanthanide oxides can be used as basis in order to adjust pH of the solution, and why lanthanide oxides, in order to avoid further complication, because we are dealing with lanthanides. Therefore, if we use lanthanide oxides for pH adjustment, there will be no technical hurdle in separation of lanthanides as compared to other bases. Now, with the dilution with water and adjustment of pH in alkaline range, thorium can be obtained as its respective phosphate, and since this is insoluble in alkaline solution of lanthanides, therefore it can be separated, and in solution we can get lanthanide sulfates, and these sulfates can be heavier lanthanide sulfates and can be lighter lanthanide sulfates, and in lighter lanthanide sulfates we dealt with cerium, and cerium was accordingly separated. So the same procedure or a bit modified procedure can be used for separation of other lanthanides from their respective solutions. Now, coming to or moving a little bit forward, so how lanthanides can be purified? For purification, the most acceptable viable method or technique is ion exchange method. And in this ion exchange method, we are using cation exchange resin. This method is rapid, it is effective for separation of lanthanides, in addition to other practical applications of this method. So lanthanides uh, can be allowed to come in contact with synthetic resin, and this synthetic resin, as I told you, is cation exchange resin. So it contains these functional groups acetate or sulfite, which are actually cation exchangers. Here is a proton, and this group possesses a proton, so these protons can be exchanged, or they are capable to give this proton in appropriate solution and appropriate medium, so they can be regarded as cation exchanger, which are present on the surface of the resin. So now this is a part of resin, and that part which is capable of exchanging only three protons. So whenever lanthanide is allowed to pass through this portion of the resin, so three protons are exchanged and this lanthanide gets attached to the resin. So lanthanide resin is obtained and three protons are obtained in solution, so they can be eluted or can be converted into other compounds accordingly as per procedure. Bonding or interaction between lanthanide ions and the resin. This is a function of size of the ion. If size of the ion is greater, then force of attraction or interaction between the two species, that is resin and lanthanide, that will be less. If size is small, then interaction will be more. So greater size, weaker interaction, and weaker size, smaller size, so stronger interaction. And in case of lanthanide, since we are dealing with aqueous solution, so we have to consider hydrated ions, and hydrated ions and bare ion. There is a difference between simple lanthanide ion and its hydrated form. Now hydration is also size dependent. Let's consider this is as an ion on left hand side of the series, and this is ion on right hand side. This is on left hand side and this is on right hand side. So on right hand side, this is, let consider this is lutetium side and this one is lanthanum side. So lanthanum, as we discussed in the lanthanide contraction, that lanthanum was greater in size and lutetium was smaller in size. So let water comes and interact with these ions. So uh, upon interaction with water, the ion which has greater size, it is capable to accommodate less water molecules, and the ion which is smaller in size, it is capable to accommodate more water molecules. So as a result, the hydrated form of smaller ion is now greater in size, and hydrated ion in for greater ion is now smaller in size. So what happened, the size of the ion got inversed. Lanthanide ion smaller in size, like this one. It has a high charge density, and this high charge density enable the ion to accommodate more water molecules. The degree of complexation is greater, and on the other hand, the greater molecule has less charge density, and this less charge density makes the ion to get bound to less number of water molecules. So this is the overall phenomena that lutetium is heavily hydrated, degree of hydration is more, and it attains greater size. And if we consider the interaction with this resin, so this ion will be less firmly bound with the resin, and this ion will be strongly bound with the resin because the degree of hydration is less, size of the hydrated ion is smaller. Now, solution of lanthanide is allowed to drop slowly down the column through the synthetic resin, and as I told you, The interaction between the resin and the lanthanide ion is accordingly created. So lanthanide ions, they are separated. Lanthanide ions are separated on the basis of their nature and on the basis of their size. So if they are greater in size, they will elute easily, and if the lanthanide ions, hydrated ions, are smaller in size, so their elution will be a little bit hard or difficult, and they will elute at the end of the process. So speed is different, and on the basis of speed, they can be separated from each other. So bond strength, it decreases from lanthanum through lutetium, as already I told you. Lanthanum is greater in size, so the bond strength is more for lanthanum hydroxide, and bond strength is less for lutetium hydrated lutetium ion. And because increased nuclear charge cause a decrease in ionic radius, and in turn increase complexation or hydration. In this case, we have to consider solution of lanthanide nitrates. They migrate to organic phase by using continuous counter current method, and kilogram quantities of lanthanides can be separated by a ion exchange resin method, and gadolinium up to 95% has been obtained through this process. This figure has been adopted from the book which I have already given to you. This is concentration on this axis, y-axis, and uh, x-axis shows volume of elute. You can also say that this is time of elution. Now, and this diagram are the lanthanide ions have been eluted through the solution as EDTA solution, through the column as EDTA solution. So lutetium is obtained first during elution process, and europium plus 3 has been obtained at the end of the process. It means the EDTA complex of europium has smaller size, and EDTA complex of lutetium and hydrated ion has larger size. So larger size will interact less with the cation exchange resin, and smaller size ions or smaller complexes, they interact with stronger force. They will establish stronger interaction with the resin, therefore they will elute at the end of the process, and such ions which are larger in size, they will elute at the beginning of the process. So accordingly they are separated, and if you look at the resolution of the graph, so the different ions can betterly be resolved from each other, and they can be separated up to required purity. Thank you very much.